Hello everyone, welcome back to Calculus BC. We're in lesson number 37, and all this lesson is about parametric equations, and now we're going to do some derivatives of parametric equations. So first thing we're going to do is the first derivative and then the second derivative. Second derivative actually is a little bit crazy, but for the first derivative it's actually very straightforward. So if you have dy over dx, remember our functions have been dx over dt and dy over dt. So those are the functions that we have. So if I look at dy, well, that would be dy over dt. Reference to dx, dx would be dx over dt, which you guys can see in the box up there. So to find the first derivative of a parametric function, you just have to take the derivative with respect to y at the top and divide the derivative with respect to x in the bottom. So let's move over to example number 9 and talk about this pretty straightforward example. It says for the curve x equals t cubed and for the function y equals t squared minus 2t, we want to find this derivative, and then we want to find horizontal and vertical tangents to this curve. Well, what we're going to do is we're going to write that dy over dt and then dx over dt. And you don't have to write this in your paper, but this is just make sure that you guys understand what we're doing here, is we're going to take the derivative of y first, just like we normally would. This is going to be the power rule. So this is going to be 2t minus 2. And then we're going to take the derivative of x with respect to t next. It's always dy over dx, so it's going to be 3t squared. And ladies and gentlemen, that is your derivative. It is that simple. All right, so let's go over here to the second part of this. Well, I want to find horizontal tangents. Horizontal tangents means that our derivative is actually equal to 0, and I'm going to do dy dx is equal to 0. So that means that for the horizontal, I'm going to set my numerator equal to 0, and this is nothing different than what you guys have done before. So we set our numerator equal to 0. We're going to get the time is equal to 1. And by time I mean t, my lord. Every video I'm going to say that. I'm so sorry. So for vertical tangents, this is going to be where dy dx is going to be undefined. So you're going to set your denominator equal to 0, and you're going to get the t is equal to 0. So that's where your t equals 0 and your t equals 1. This is where horizontal and your vertical are. So let's shift gears and talk about the second derivative. And it's just a little different than what you have seen before. We're going to use the chain rule here. So we're going to set dy, the derivative of dy dx. So d over dx of dy dx. So what they do here is d over dx actually can be represented as d over dt times dt over dx. And that's what this is. So d over dx, again, if we were to cancel these out, that's what that is. So what this is showing you is that we're going to multiply d over dt. So let me actually change the color for this one. So we're going to take d over dt times dt over dx, and we're going to multiply it by the derivative of dy over dx, which we've already established what that was, right? We already talked about that up here. It's going to be dy over dt over dx over dt. Well, what ends up happening here is that we're going to have the d over dt in the top. This is the derivative with respect to t of dy dx. And then if we do this, we divide, if we are multiplying by dt over dx, we're going to actually divide by dx over dt. So what this is saying, and that's what you get right here in this chart. What this is saying, ladies and gentlemen, is simply this. You're going to take the derivative of your first thing, like you normally would. So we're going to use the quotient rule here, and we're going to do it with respect to t. So we don't have to worry about implicit, because all of our functions are already in t. So we're going to take the derivative of dy, because this is equal to dy over dx, right? So we're going to take the derivative of this with respect to t. So that's what the top means. And then we're going to divide. Once we do that whole thing, so once we use the quotient rule in this thing, we have to, and this is really important for all of you guys to know, you will then also divide by the derivative of what x is. All right, what the derivative of x is. So let's refresh our memory. So x is equal to t cubed, and y is equal to t squared minus 2t. And then again, you guys can see up here that the dy dx that we found in part A was 2t minus 2 over 3t squared. So if we want to find the second derivative, so d squared y over dx squared, we're going to take the derivative of this with respect to t. That's what this means. So we're going to use the quotient rule, and we're going to get the denominator We're going to multiply by the derivative of the numerator, which is just going to be 2. And again, it's with respect to t, so it doesn't matter. It doesn't matter. There's no implicit here because everything's all about t. Minus the numerator times the derivative of your denominator, which is going to be 6t, all over your denominator squared. Then we're going to, and that's this piece, then we have to take the derivative with respect to x, which we've already found. We've already found what the derivative with respect to x is. It's right here, right? Or the derivative of this guy. So it's just going to be 3t squared. So this is the actual derivative, second derivative of a parametric function. So bottom line is you will always, always, always take the derivative of your parametric function by doing dy over dx, and then you will then divide that by the derivative of dx. And again, that works out based on how we broke down this, this equation, or this expression, I should say. And so when we start simplifying, and we're going to do that now, we're going to get, because it's going to ask us to discuss the concavity of the curve, because there's so much layers to some of these questions. So we're going to go ahead and distribute, well, I'm going to go ahead and multiply the 2 times the 3, which will get this. And then I'm going to distribute the 6t, like so, all over 9t to the 4th. And then I'm going to just go multiply by 1 over 3t. So I haven't really changed that up, right? It is what it is that you guys can see right here. And when all is said and done, we're going to get negative 2t, because again, this video is not to show you how to simplify stuff. You guys can do this on your own. And I probably should have left this actually as 3t squared, quantity squared, because I'm going to rewrite it again as to the cubed, because that's really what this is. So I probably shouldn't simplify that. Now I'm looking at that problem. So I get this. And so this is going to be my second derivative. This is my second derivative. So if I'm talking about concavity, well, I've got a lot of values here. I have critical values that we talked about where t equals 0. I got a critical value at time equals 2, and again, t equals 0. So at t equals 0 and time equals 2 are all my critical values for this function. So I'm going to go ahead and I'm going to change the color one more time here. We're going to do d. We're going to plug into our second derivative. Remember this, we have our critical values is at 2 and 0. If we plug in 0, then we're going to get, well, this is the value. Obviously, if we plug in something like 1, we're going to get a negative, and the negative is a positive and a positive. So we're going to get a positive here. If I plug in something like 3, I'm going to get a negative, a positive, and a positive. If I plug in something like negative 1, I get a positive, I get a negative, and I get a positive. So there you go. So concavity, we're going to be concave up from 0 to 2. And we're going to be concave down from negative infinity to 0 and from 2 to infinity. And, sometimes people like open and close brackets. It doesn't really matter for that. So that is the idea that we want to do for this particular problem. So I hope that makes sense. And we're going to jump over to example number 11 to do another second derivative thing. So this one says find the first 2 derivatives of the function determined by x equals 5 cosine of t and y equals 4 sine of t. And we're given the restriction of 0 to 3 for t. And then we want to evaluate them at pi over 6. Well, first thing we want to do is find the first derivative. Well, that's just dy over dt, dx over dt. So we're going to take the derivative of this, like we normally would. So it's going to be 4 cosine of t. Awesome. We're going to take the derivative of this. Well, it's going to be 5 times negative sine of t. And so what I'd like to do here, so I don't have to use the quotient rule, and we're really good with our trig function derivatives now, is I'm going to rewrite this as negative 4/5, and then cosine over sine is going to be cotangent. So I'd rather take the derivative of cotangent than have to do stuff like this. Now, if you don't remember what the cotangent pi over 6 is, and, we can talk about that another time, but the cotangent of pi over 6 is just going to be the square root of 3. So if you don't know it, so this is your first one. If you do not know this, then what you could have done is you could have done cosine of pi over 6 and then negative 5 of sine of pi over 6. And could have done 4. This is the square root of 3 over 2. This is sine of 1 over 2. And then you got the square root of 3 here when it's simplified down. But bottom line is we have our answer. So we know that the first derivative at pi over 6 is going to be negative 4 square root of 3 over 5. And that looks really horrible, but it is what it is. So I'm going to go ahead and erase with a bigger eraser here. I'm going to go ahead and erase this. And let's find the second derivative. Find the second derivative. So the first thing we're going to do is we're going to take the derivative with respect to t of negative 4/5 cosine of x. And then we're going to also take the derivative of x with respect to t, which we've already done. It's sitting right there. So we already know that our second derivative, our denominator is going to be negative 5 sine of t. And I'm going to stress that. I'm going to stress that with you guys, that it's going to be negative 5 sine of t. And then this is just our derivative of our top. So it's going to be negative 4 over 5, and then the derivative of cotangent is going to be negative cosecant squared of x. And that's what I said. It's so much easier to do it that way than have to do. If you guys are not comfortable with derivatives of cosine or cotangent or any of the reciprocal functions, then just do your nice little quotient rule thing and then simplify it. Beautiful thing happens here is the fact that these are going to cancel out. And if we were to just simplify this a little bit more, we're going to have, this is going to be 4 cosecant squared x over 25 sine x. Well, another thing that I like to just personally do here is notice that there should be that negative, right? There should be a negative here because I haven't got rid of that one. That cosecant is sine. It's one of our sines. So you really could have, before we simplify this down, you could just write this as sine x times 1 over sine squared x, because that's exactly what this is. And so again, if you're not comfortable with plugging in, functions for this, or what the pi over 6 of the, cosecant squared is, then you can just do as this. So this is the second derivative of our function. So it's negative 4 over 25 sine cubed of x. And in this case here, we're going to plug in pi over 6. So we're going to get negative 4, 25. The sine of pi over 6 is going to be 1/2. So 1/2 quantity squared is going to be 1 over 8. All right, so it's 1/2, so quantity squared is 1 over 8. And so we can go ahead and just multiply and we get negative 32 over 25 is our answer. So this is the second derivative of our function evaluated at pi over 6. Okay, so that's my video for this one. I hope that makes sense. But again, ladies and gentlemen, the stressing of this video is not what I just said there. The stressing of this video is to make sure that when you take your second derivative, that you still take your derivative of your top and your bottom, which you get here, and you're going to have a quotient rule, right? Because it's going to be the derivative of the y over the derivative of x. So you have a quotient rule, and then you're going to divide by the derivative of your x with respect to t. So we're going to leave you guys there for that one, and I will see you in the next video.